Hi everyone, Mrs. Basega here, and today we're working on the Unit 6 review packet. So we start off the unit with this idea of electrostatic force, and that's the force between two charged objects. The direction of that force depends on just the sign of the two charges. Think like opposites attract, like if one is positive and one is negative, they'd attract each other. So this electrostatic force only depended on the sign of the charge, whether it's positive or negative. It doesn't depend on the magnitude of charge. Now, the attracting force occurs when the two charged objects are of opposite signs, D. So positives attract negatives, and vice versa. Now, we studied this by doing an experiment on pivot. This is the experiment where we were lowering two charged spheres closer and closer together and measuring the force with a scale. If we had increased the object's charge, that would have resulted in more force. So which graph shows that if charge goes up, force goes up? That was graph C. And if I were writing the axes titles, I would put charge on the x-axis, and the charge causes an increase of force on the y-axis. Now, what happened when we moved the spheres farther and farther apart? Did the force increase or decrease? It decreases. Now, here's the tricky thing. The remaining three graphs all show that as distance increases, force decreases. But only one of them is the right shape. And this is a very important shape. This is the shape called an inverse square. So these two graphs, if you had to include a graph on your note sheet, those two graphs would be really important because those two graphs show the relationship between charge and force and distance and force. It is from these two experiments that we get radial distance squared in the denominator and the charge in the numerator. Since there's two objects, I need to see two charges, so charge 1 and charge 2. And these two equations together explain why the electric force is kq1 q2 over r squared. So now let's use this equation. This equation describing the size, the magnitude of electric force, this equation is called Coulomb's law. And what it says is if you increase the distance, you're going to decrease the force by a square. So let's do number 5. Number 5 says we take two charges that are 2 centimeters apart, and now they're 10 centimeters apart. Well, first off, how much farther apart is 10 than 2? It's 5 times farther apart. So if I make R 5, it's 5 times bigger than it was before. I know force should decrease, making the two charges farther apart. Imagine like taking two magnets and moving them farther apart. That will make the force decrease, so it can't be A and it can't be B. But since it's 1 over r squared, I want you to think of putting in the 5 for r. Right, leave everything else 1. But if I put in the 5 for r, because it got 5 times farther, well, that's 1/25. So that answer is D. That's what an inverse square means, is if you change radial distance, it will be that change squared that it decreases the force by. So next in the unit, we moved on to like the review of chemistry, and we talked about like the different parts inside an atom. The negatively charged particle in an atom is the electron. Sometimes people look at it real quick and be like, oh, Ne negative, Ne neutron. But no, neutrons are Ne because they are neutral, not negative. Neutrons and protons are both in the nucleus. So we know that is true. Protons and neutrons are both in the nucleus, so maybe I put some P and N symbols in here. Okay. Electrons and protons have the same magnitude charge, and if you get tripped up on the word magnitude, I want you to think size. Both electrons and protons have the same size charge, except one is positive and one is negative. And you don't need to know this number off the top of your head, but they both have a charge of 1.602 times 10 to the negative 19th coulombs. A very, 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 very small fraction of the coulomb is one electron or one proton. What they don't have is they don't have the same mass. Electrons are out here in an electron cloud, and they're very, very light, right? Protons and neutrons both have the same mass. They are heavy. They're approximately the same mass. They're very, very close together. So C is true and B is false. Electrons are light. Protons and neutrons are heavy. And those reasons are why when you pass charge from one object to another, that it's because of moving electrons. Protons are too heavy. Neutrons are too heavy. Neutrons don't even experience the electric force. And nuclei, well, nuclei means protons and electrons. So if protons and electrons, nuclei means protons and neutrons. So if protons don't experience this force significantly and neutrons don't either, then neither will nuclei. When electrons move, we call this electricity. When you comb your hair and the comb becomes positively charged, well, this causes static electricity. Your hair will become staticky. And think of it like this by conservation of charge. If the comb becomes positively charged, and I can't draw a comb, so forgive me, this box here, that's the comb. And your hair, here's your beautiful hair, right? That must mean the comb's electrons went into you. Your hair will now be negatively charged because it has more electrons than it did before. This is conservation of charge. The electrons moved from the comb to the hair, but there's the same number of charges overall. If we started with 5 electrons and 5 protons, and 5 electrons move over here, then surprise, this has a charge of -5, this has a charge of +5, but the net charge of 0, because it was neutral to start, stayed the same. So now let's work a more complicated example. So a positively charged rod is brought near a sphere. As a result of this positively charged rod, the sphere's electrons will move left. So I'm going to draw electron flow to the left. Remember the sphere's protons stay still, so I'm going to draw 5 stationary protons, but its electrons want to go left because it's trying to get towards this rod. This is because electrons are attracted to positive charges, and the protons stay still. Well, notice the sphere is still neutral, C. There's 5 electrons and 5 protons, the electrons just moved left. The sphere attains this charge because the sphere is polarized. No charges were transferred off or onto the sphere, right? Those electrons are still on the sphere, they just moved left. So no electrons were lost and none were gained, so the sphere is polarized but still neutral. This creates attraction. And a good thing to add to your notes then is whenever something is polarized, it always causes attraction. Now, why is that? It's because when electrons move, they always move to react towards some nearby charge. And that always results in the half that's nearest the charge, well, having the opposite charge. Here's what I mean by that. Imagine I cut this sphere in half. And let's say this positive charge goes to the right-hand side. So on the right-hand side, I have a charge of +3. 1, 2, 3. On the left-hand side, I have 5 electrons and 2 protons. The left side of the sphere has a -3 charge. It will get attracted to the nearby rod. And so polarization always causes attraction. So let's see what that looks like with field. Field is the distortion of space around any charge. Field points from positive towards negative. So the only one that meets that scenario is A. A shows the field lines pointing away from positive charges. B shows them going towards the positive charges, so that's not true. C shows it going towards positive charges, that's not true. D, your field lines don't start or end on this charge, so that's not true. D is a good distractor because when we get to magnetism, magnetic fields will form circles. Electric fields don't. Now, of the electric fields you have to know how to do, be sure to be able to draw 2 positive charges, 2 negative charges, a dipole, or a capacitor. A capacitor is a really common configuration. Notice that those field lines go from positive to negative. Notice that they are equally spaced lines, and because they are equally spaced lines, there's all the same field strength. This is really commonly tricky because when people look at this, they're like, oh, well, doesn't Q have a stronger field because it's closer to the positive side? No. Look at the field lines. The stronger the field lines, the closer the line spacing. But if I say that backwards, if everything has the same line spacing, then everything has the same field strength. All 3 of these points show equally spaced field lines and therefore experience the same magnitude of electric field. Now, electric potential energy occurs where whatever particle you're considering is repelled the most. Where is it most unstable? Where does an electron, like in number 16, least want to be? It least wants to be at R. They're like, okay, the electron would most repel from part R, so point R is where the electric field, or the electric potential energy would be greatest. Same with the proton. Where would the proton most want to repel? Q. The proton does not want to be there. So Q is our answer for number 17. All right, so up to here, that was all our short, multiple choice problems. Now we're gonna get into some math, drawing, and explanations. Come back and look at the full answer key at some point. This video is gonna see me write shorthand, so you're not watching me write all these words. So please, come back and read the actual answer key after you watch this video. So for number 18, 2 charged objects are placed near each other to start. If the distance increases by 4, how much weaker or stronger does the force become? So I know I'm making the radial distance 4 times bigger. So imagine I'm taking that electric force equation, KQ1 Q2 over R squared. And imagine I make everything else 1, except for the 4. So radial distance, I put in a 4. Guys, what is 1 over 4 squared but 1/16? This will be 16 times weaker than the original force. Now that makes sense to me because the farther apart my 2 charges are, the less field they'll experience, the less force they'll experience. Just like moving 2 magnets farther apart. So let's try this method again. If the charge on one object doubles and the charge on the other object triples, I know I'm expecting this force to increase. So I'm going to write down the original equation, KQ1Q2 over R squared. I'm going to put everything in as a 1 except for Q1 and Q2. I'm going to put that in as a 2 and a 3. 2 times 3 over 1, that's a 6. This makes 6 times more force than original. And that makes sense because imagine I make one magnet stronger and one magnet stronger. The total force between them would also be stronger. Last time, and we'll go a little faster. So if the charge on one object doubles, the charge on the second object triples, and the distance between them quadruples. I'm actually making 3 changes at once, so it's really important to write down the equation. That makes sure I substitute everything in the right place. Imagine the K is the 1, and I'm putting in a 2 for Q1, a 3 for Q2, and over 4 squared. And for these proportion problems, feel free to leave this as decimals. I'm not going to do this in my or leave this as fractions. I'm not going to calculator this. 6 over 16. This force is weaker than the original force. And I can tell because whenever the force is weaker, this ratio will be less than 1. It's 1/16 of what it was before. Over here, this must be stronger because this is greater than 1. It's 6 times stronger than it was before. So 6/16 is weaker because 6 is less than 16. It is 6/16 of its original force. So be able to deal with this equation with the graphs, these graphs, write them down. Be able to do it with proportions. If I asked in both the multiple choice and the short answer, do it with proportions. And actual calculations. So let's make this happen. All right, actual calculations. If I have a charge of -3 and +6, these attract each other. These attract because opposites attract. And like I said, I'm not going to write out all the words here. You can go check the answer key for that. These attract because opposites attract. That means the force on Q2, oh, there's a typo here. Q2 is supposed to be this one over here. Has a charge of 6, not 9. It'll get fixed on your copy, no worries. So the force on Q2 is left because it's attracting. Calculate the magnitude. Magnitude means size. A vector has a magnitude, which is some number or size, and a direction, left. So write me the equation for electric force. That's KQ1Q2 over R squared. K is 9 times 10 to the 9th. Always, always, it's a universal constant. Q1 has a charge of -3. Q2 has a charge of +6. And guys, if you want to absolute value these charges, feel free to do so. Makes my life easy, makes your life easy. And they're a distance of 0.2 meters apart. But that's 0.2 squared. Now, when you plug this into your calculator, it might say something like 4.050 E12. That E is telling you the powers of 10. So I might give you a choice that says 4.050 times 10 to the 12th. That E is telling you how many zeros this number has. And I know you don't need to, but just in case you don't know how scientific notation works, I want you to imagine we have this number, so 4.050. And I put a very large number of zeros on this side. To count how many zeros this would be, I start with where the decimal place is, and because the 12 is positive, I'm going to count 12 to the right. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. One more zero, not going to fit on the page. That's how many zeros this number has. So when I say the electric field is electric force is much stronger than the gravitational force, these two silly small charges 0.2 meters apart are giving me a huge force. Now, which has the greater magnitude of force? The same. Notice how I drew these as equally sized in opposite directions. I even put equal marks here. That's because Q1 and Q2 make up a force pair. So Q1 pulls Q2 to the left, Q2 pulls Q1 to the right. These are equal and opposite by Newton's third law. But if you need more proof, notice that if I do this same equation for charge 2, it would be 9 times 10 to the 9th times 6 times 3 over 0.2 squared. Switching the order of these two doesn't switch the final force. So both experience the same force because the charges are a force pair. They obey Newton's third law, and mathematically, you'll see that they're equal. So for instance, in number 20, where like the proton is attracting the electron, well, these experience the same size force. They experience the same size force, but the proton is so heavy that it barely moves, but the electron is light, so it moves a lot. This electrostatic force, which I guess you can call the electric force if you want, is the centripetal force that causes the electron to orbit the nucleus. Notice that the electron is pointing towards the center. So this is both the centripetal force and the electric force. So when it says calculate the centripetal force between the electron and the nucleus, I would be taking this Fe equals KQ1Q2 over R squared. I'm putting in K is 9 times 10 to the 9th. I'm putting in the charge of the electron, that's 1.602 times 10 to the negative 19th. And the charge of the proton is 1.602 times 10 to the negative 19th. Right. Notice when I absolute value the charge on the electron here, it just makes this front negative into a positive. It doesn't change this negative 19 because that's the power of 10. That's not an actual negative sign. It's just telling you where's the decimal place. Now, this is all over R squared, where R is 5.29 times 10 to the negative 11th squared. So we go calculator this. This time I get a really small force. Now, why do I get a really small force here where I got a big force before? Well, that's because when I originally solved the other Coulomb's law problem, a 3 and a 6 Coulomb charge, well, that's billions upon billions of an electron. Well, what if I only have one electron and one proton? This force is really small. It's 8.25 times 10 to the negative 8th newtons. They both experience equal and opposite forces. It's just that the electron moves faster because it's lighter. But hey, electron definitely attracted to the nucleus because opposites attract. The nucleus isn't neutral, it's positive because its nucleus is literally just one proton. It's the easiest atom that's out there. One proton, one electron. That's it, hydrogen. Now, if this proton suddenly decayed into a neutron, well, that electron would lose its centripetal force. And let's say it was traveling counterclockwise, then the electron would continue to go in the direction of its tangential velocity. Its inertia wants it to keep going in a straight line. And without the centripetal force, it would just keep going in a straight line until something stopped it. An object in motion stays in motion. All right, so we calculated forces, we did that again. Now let's talk about charges moving. So Ben Franklin is charging this glass rod by friction. So it starts neutral. So read the thing to know that it starts neutral and neutral. So the charge on the silk before the materials are rubbed together, it's neutral. Before things are rubbed together, most objects are neutral. That's why we don't experience a lot of electrostatic forces unless something else happens to them. So the glass rod is now positively charged. That must mean the glass lost electrons to the silk. So if there should be 1, 2, 3, 4, 5 electrons in the rod originally to make that neutral, and 5 electrons now go into the silk, this silk should now be negatively charged with a charge of -5. So after the charge is going to be negative because charging by friction still conserves charge. The total charge was neutral to start. The total charge is still neutral. +5 cancels -5, total charge is still neutral. The larger net charge is the same. Both the silk and the glass have a charge of 5, so larger net charge. Imagine I'm like absolute value in this. These have equal and opposite charge. The silk gained 5 electrons to become negative. The glass lost 5 electrons to become positive, so equal and opposite. All right, so charges are moving still. Calculate net charge. There are 1, 2, 3, 4, 5 electrons with 3 protons. This has a charge of -2. If a person touched the sphere, the electrons would flow out of the sphere. How do I know? Well, a person touching the sphere, this is key word to mean grounding. And grounding, because the person is on the ground, they provide a safe pathway for the electrons to move off the sphere into the ground. And they're going to do this, so my electrons are going to flow in this path until it's neutral. Well, to make this neutral, the electrons would flow out here. So let's say 2 electrons flow out to the ground. That's my ground symbol. 2 electrons flow out to the ground to make it neutral. If you are having trouble with this one, the definition you want to write down is grounding. Grounding is when a big object, like a person, touches a charged object, like this sphere, and provides a pathway for electrons to either flow in or out of the object. Right? In this case, it's flowing out until it becomes neutral. Ta-da! Now, electroscope. We didn't have enough that everyone could play with this as a demo. I did this demo in person in class. So if you need to go see this again, ask me to show you how the electroscope works if you're stuck on number 23. So a negative balloon touches the electroscope. That touch is charging by conduction. Because they literally touch, electrons from this balloon will flow down into here, making the top neutral. So notice these negatives are now like neutralizing the positives. But notice that the original 4 electrons then flew down here. The leaves of the electroscope move apart because this piece of metal is negative, that piece of metal is negative, so they repel each other. And overall, let's say just the sphere, I see 1, 2, 3, 4 protons and 1, 2, 3, 4, 5, 6, 7, 8 electrons. That is negatively charged. So what are the key words I can look for to distinguish this one? When I see the word touch, in this case, a charged object touches the electroscope, I know in the back of my head that means conduction. I can tell it's not grounding because in the grounding case, this was a neutral person does the touch. Keep that in the back of your head. That is a good note to write in that handy dandy note sheet of yours. All right, electric field. The electric field from Q1 and Q2 distort the space around them, creating these electric field lines. Electric field lines point away from positive charges so Q2 must be positive, and towards negative charges, so Q1 must be negative. I know this because the charges have field lines pointing towards Q1. Of the points A, B, C, and D, the one with the strongest electric field is A. This is because A has the closest together, most dense field lines. Notice that A, that like, if I drew a little box around A, it has 1, 2, 3, 4 field lines going through it. If I put the same size box around B, it only has 2. A has the lines closer together, so it has the strongest field. So where should an electron be placed to have the most potential energy? An electron needs to be placed where it's going to repel the most. It would repel most at A because Q1 is negatively charged. So knowing that Q1 is negative allows you to answer this question. An electron placed at A would be most repelled. Wherever you are most repelled, most unstable, is where the electrical potential energy is the greatest. It has the most potential to move. So if I do that question here, a proton would have the highest potential energy at A because that's where it's most repelled. A proton placed at A would really want to move away from that positive charge. An electron would be most repelled at E. It doesn't want to be near that negative plate that it is so near. But what if I put them in the middle? If I put an electron at C on this side and a proton at C at this side, they both experience equal and opposite forces, right? I drew my arrows wrong, but we'll live. I'll fix that on the actual key, right? One wants to go down, one wants to go up. These are equal and opposite forces, but they would hit the plates at different times. That's because even though they have the same force, the speed is determined by the acceleration. The force is the same, but they have different masses. The proton is heavier, so it accelerates slower. So the proton will take longer to hit the bottom plate, and the electron would get there first. Cool. So finally, an electron is placed at E and released from rest. The items in the system are the electron, the capacitor, at E, the electron would have a lot of potential energy. It's like very, very repelled. It's like, no, we don't want to be here. Oh no. At point A, and it actually doesn't matter the path it takes, just that as it travels, it will get faster and faster and faster because that potential is turning to kinetic, right? In that very common trade-off when energy is conserved. If all that potential turns to kinetic, well, I did 3.5 boxes of potential. Let's do 3.5 boxes of kinetic. Conservation of energy shows those two should be equal to each other. Now it's come to my attention that this is a slightly older version before I fixed and added one key important thing. I mentioned this earlier, that you should be able to draw the electric field of 2 positive charges, 2 negative charges, a dipole, 1 positive, 1 negative, and a capacitor. So hey, let's get that dipole drawing in. It's the only one that we have not seen yet, and we'll make sure it's good. So on your copy, this might be number 25. I added it in for a reason, wink, wink. I wanted to make sure you could draw a dipole. And when drawing electric field, you want to make sure your electric field lines fill up the whole area. You have a reasonable number of them, so I normally do like 4 or 5 per, and a dipole means equally numbered field lines here. And I know they attract each other. So away from positive towards negative. Make sure you draw arrows. If you don't draw the arrows, I don't know what direction you mean. So my field lines are leaving the positive charge, going towards the negative charge. I'm going to do this till it reasonably fills up the space. Right? Something along these lines. Away from positive towards negative. And let's check. I have a reasonable number. It fills up the whole space. It points from positive to negative, and field lines don't cross. Right? So, be able to draw the dipole configuration like this. Be able to draw two positives, two negatives, or the capacitor one, where it points from the top plate or from the positive plate to the negative plate in nice, equally spaced lines. You don't have to worry about drawing the outside behavior. All right, everyone, best of luck.